Good morning. Welcome to the webinar regarding the integration of the NIR with the PharmaTech blender. We'd just like to say thank you. We're in partnership with our supplier, VRV, and PharmaTech, the blender manufacturer. So this morning is myself, Darren. I'm the product manager for the Near systems at SciMed. Also is Sean from PharmaTech. There will then be a live or recorded demonstration followed by software demonstration from Emiliano. So we represent VRV and the Near range of NIR spectrometers. This generally consists of three main products. First one being the on-site W. This is a handheld device. This is ideal for in-field, at-line or offline measurements, and it's very well suited to material identification. This is a Bluetooth device. It's also got the ability to be connected to the communication PC or laptop or tablet using a USB, but it's also built in with a 10-hour battery. You tend to find the devices that it's connected to battery runs out before the actual NIR, and it's also IP rated, so it's ideal for a warehouse environment. Today we'll be focusing more on the process analyzers, where we have the PAT-U, which is a wired version, and the PAT-W, which is the wireless version. Both systems are a ruggedized process monitoring instrument designed for factory applications. The PAT-W is either a wireless instrument, hence why we're talking about it today. It fits in very well for tumble blending, but it's also got the ability to be connected via Ethernet. So if you do want a static measurement position, you can connect via Ethernet and power. And again, the battery is an 8-hour battery, so will generally last longer than the process itself. And it also has inbuilt the multi-axis sensor, which makes it ideal for triggering in such application as blending. So this is the device that we'll be demonstrating today, the PAT-W. The great thing about the Near product range is that we do generally have a device for every part of the process, from the raw material identification to the any pre-processing that you may do, the actual blend uniformity in this case, followed by any other processes that go on after, right through to the actual product release as well. The Near technology is all centered around this linear variable filter. It's about the size of a grain of rice. And the great thing about this LVF is on a hard, dense glass. It's very stable. It has a long life, so it makes it a very robust sensor, and obviously it's very useful in applications such as NASA missions, for example. So we're utilizing this technology. It's a small form factor, so this obviously gives it opens up some unique applications. It has a very long lamp lifetime, greater than 40,000 hours, and there's no need for any laser or moving parts. The great thing about this statement is that there's 100% transferability between units. So any method that you develop on one system, you can easily transfer that to another system. And the great thing about this system also as well is there's no fiber optics. Fiber optics can be expensive and has a tendency to be affected by temperature variations as well. The software behind every good system needs good software. The software is a very intuitive app-based field software, and it's very clear display characteristics, such as the process monitoring diagrams as well. So we can use the Near in all these processes. The data comes back to a central computer, and then we can link this up to the company server as well. So it gives it a fully integrated PAT system. So the PAT-W is an ideal system for blend uniformity, drying, granulation, API content, identification, and much more. But today we're more interested in the blend uniformity. We all know that if you have a variable in, into a fixed process, you will inevitably get a variable output. What we want to do is use the ability of PAT to vary the input, vary the process, and have a consistent output. So using this micro NIR PATW, we can attach the micro NIR sensor to the lid of a blender. The trigger mechanism activates once the micro NIR turns to the 3 o'clock position on the blend, and then we aim to have a delay that is in keeping with a spectral whereby the material is on the lens of the micro NIR. A blend starts obviously by loading the blender. You have the first few cycles, and hopefully eventually you will end up with a good blend. What we want to try and move away from is the possibility of over blending. So one of the easiest ways to represent the data is something called moving block standard deviation. You can predefine the size of the moving block. In this case, it's a five moving block. So we compare the spectra 1 to 5, then we compare the spectra 2 to 6 and 3 to 7 and so on. This is the raw data from just a typical blend. And you can see that the green line there is the convergence of the NIR spectra as the blending proceeds. Quite often we do some pre-treatment of the data, in this case being an SNV and a first derivative. And then when we plot the moving block standard deviation, you see the initial mixing stage, followed by hopefully at some point a nice steady state, and we can define the endpoint. The great thing about the NIR is that you can use it quite easily from the design process to be able to see how altering various different bin sizes, fill levels, the speed at which you blend, and also the way in which you load your blend. You can quite easily compare the subsequent method changes that you do. And then taking the calibration further, we can look at things like principal component analysis to map the process trajectory of the blend. Now I will pass over to my colleague at Pharmatech, Sean, and he will now go over the hardware of the blending.
Okay. Good morning. I'm Sean Redden. I'm the operations manager at Pharmatech. I've been with them for about 5 years, initially as quality and documentation, and I've been involved in most of their development projects over the past 5 years as well. So if you have any questions about the blenders as we're going forward or at the end of this, then please feel free to pick my brain. I'm going to try and cover the more mechanical aspects of integrating NIR PAT into a tumble blender today, as Samed and Viavi will concentrate much more on the chemometric side of the equipment. I'm covering the how do you actually fit it. So who are Pharmatech? We basically provide bespoke engineering solutions. So we have a base range of blenders, of which I don't think I've seen the same one leave twice. We will customize anything to suit your specific requirements. And we work very closely with a company called Connection Systems, which offer all of the polymer type products like hoses, flexible ducting and sampling systems as well. But skipping past the sales pitch, as I mentioned at the start, I'm going to be trying to cover the mechanical aspects and then looking more into the communication considerations that are required for integration as well. So to get started, I think we need to have a quick look at the basics of blending. Blending is obviously it's a surface phenomena as the particles tumble down the slope. So you end up with a mixing layer on the top, as you can see in the small GIF there, with a static layer underneath. Now there's variables even at this stage that need to be controlled or accounted for, and that is the particle size, particle mass, and particle shape. And altering any of those will have an effect on your blend efficiency or viability. The way we always like to describe this is to talk about the parable of the sports balls. So if you think of half filling a drum with tennis balls, and then adding in some cricket balls on top, if you were to then rotate that drum, where would you expect the cricket balls to end up? If you then to put footballs into the same drum with the cricket balls and the tennis balls and rotate again, where would you expect the footballs to end up? And that's the aim before you of your pre-processing, before you've even started to fill your vessel, is you want to try and get as similar a size, mass and shape as possible to reduce that blend time right down. So there's two main methods for integrating NIR into a tumble blender. One is along the rotation axis so that you can effectively continuously sample, and the more common approach is the perpendicular to rotation axis. It's a much easier method of integrating engineering wise, but it only allows you to take one sample per revolution. It seems that I jumped off topic slightly there, but why are we looking at the different methods before we move into the other parameters? It's because your process parameter will dictate which method suits you. If you don't fill up to 50% of the vessel, then you can't go along the rotation axis, because you won't be able to see powder continuously throughout the blend. The fill volume is one of the key, the main variables that we found that dictates the blending efficiency. We work to an optimal rule of thumb, usually of around the 50% mark, but you can get away with between 33 and 66%. If you go above that 66%, there simply isn't the free space, and if you go below the 33%, it tends to just slump around the outside of the vessel. This obviously greatly depends on the vessel's shape and the asymmetry that shape introduces. There's also additional features that you can put inside of a vessel, such as baffles or some sort of intensifier agitation, which again will increase or decrease your potential fill volume. So we're considering this for integration, because if you're working on the rotation axis, you obviously need at least a 55% fill to ensure that the sensor is covered at all times. And this is much more suited to a full-scale production, sort of 500 to 1,000 litre plus sized vessel. Once per revolution, it doesn't matter whether you're working at 33, 66, or if you've got agitation in there, you can get all the way up to 80, 85% fills. But you're then limited, especially on the small. This is much more ideal for the smaller blenders, and then your only limitation is actually fitting the vessel and the NIR device inside your guarding. Okay, I mentioned on the last slide about the asymmetry that the vessel can give. Obviously, you need some asymmetry to improve the blend, but you have to consider the vessel shape and the location that you're going to fit the NIR unit. If you're putting it on a drum lid, it's nice and simple. But if you've got V shells or IBCs with offset stub axles, you do have to consider whether the location of that NIR device and making sure that it is covered once per revolution. Okay. So as I mentioned, drums are really the simplest to modify by adding a ferrule onto the lid and doing a once per revolution approach. If you wanted to go through axis, we would not recommend doing that on the drums. IBCs, we can put it on the lid, on the side, through the stub axle. It all depends on your process and the type of vessel that you're going for. V shells, we will usually put that on the lid because the base flange will usually have a valve on, especially on the larger V shells. Through stub axle sort of along the rotation axis through stub axle for V shells is less commonly done. Considering the blend speed when you're fitting an NIR device, too slow and you'll slump, too fast and you'll centrifuge. That's the parameters that you're trying to refine, and that's one of the things that you'll be using the NIR device, especially in the early stages, to work out which speed to use. When integrating the actual device, we're interested in this as if you are slumping, you're not going to cover the sensor, and if you're centrifuging, you may be permanently covering the sensor with a single portion of the powder. So you do still need to try and aim for the sort of the perfect tumbling action in pictures 3 or 4 there. The speed also has quite an impact on the triggering method, but we'll come on to that on a later slide. Okay, so we've quickly gone over the parameters, the variables for a blend there. So fill volumes will have the greatest effect on the integration, because we've got to make sure that the sight window is covered. You do need to consider your vessel shape and the blend profile, because they come a close second. And it's unlikely that the blend speed will actually cause slumping or centrifuging at the speeds that we're going to that blenders will typically be able to output, your 3 to 30 RPMs. But if you are running below that 3 RPM, or you're running at 40 to 50 RPM, then you, especially again on lighter powders or smaller blenders, you are moving into territory where you may witness this. Okay, so what's the main pros and cons of working through shaft or along the rotation axis, or perpendicular to the rotation axis? In fact, not the pros and cons. Jumped ahead of myself. What are the main methods for going along the rotation axis? So the easiest way of integrating that is through a stub axle, or as you can see in this image here, where the actual NIR device is fitted inside the drive unit, and the vessel will have a window on it that couples with this. Alternatively, you can attempt to externally mount an NIR unit on the outside of the vessel, and just making sure that is on the center of rotation as you're blending. The simpler approach is the one sample per revolution, the perpendicular to, where your NIR unit is simply fitted on top of the vessel, or even on the side or base flange, depending on what the before and after processes are. So the main consideration when you're doing this is the focal length of the device you're using. You can have contact focal length, so probes effectively that go through a seal, a diaphragm into the vessel, as you can see in the bottom left-hand corner. Short focal length, which is what the micro near PAT W is, which is where it's in contact with the vessel lid, but then the lid accommodates the standoff, the distance that's required. Or a long focal length, as you can see in these middle images here, where the NIR device is effectively just looking through a window on the side of the vessel. This is just a few more images of examples of how it can be integrated into vessels. The top left one here shows a long focal length with an agitator, so it's effectively a double-sided drive unit. This was to allow continuous sampling, but with a long focal length, so the actual device rotates at the same time as the vessel, with all communications running back through a slip ring. Or that for the short focal lengths, you've again got lid attachments. This is a V-shell lid in the bottom left. You can run a short focal length through a stub axle, or even run a probe through a stub axle if needs must. Okay. So along the rotation axis, that gives you a continuous set of samples, which can allow you to use much larger and more accurate sampling equipment. However, it tends to cost more because every vessel that you're using, every vessel body will need modifying to allow it. And modifying the vessel body tends to be a much more complex fabrication than the vessel lids. However, one of the key benefits is that the spectrometer is actually static, so it will reduce, or it's protected during handling, and it should reduce any potential damage by operators. Once per revolution, though, is a much cheaper or a much more cost-effective approach, because we can usually just modify the lids, and lids are often interchangeable, so you can often have one lid to suit 10 different vessels if needs must. It allows you to use the gravity switch, so there is a much lower amount of control integration that's required. We'll come on to the control integration shortly. But it is often limited by the size constraints of the blend area. Obviously, you're taking the blending vessel, which would usually fit tightly within the guarding. So for a blender that would usually have a 30-litre capacity, it might reduce this down to 25 just because of the space constraints. Throughout the last few slides, I've kept talking about it seeing into the vessel. How do we do this? We fit a sapphire window, which is considerably harder than glass, but not quite as hard as diamond. And we select sapphire because of its optical transmission. It's a 21 CFR compliant material. With the way we mount this is that we'll effectively bed it into a food grade silicon adhesive, which is a formed in place gasket. Gives you a completely smooth internal surface. So if you aren't using NIR, the lid can be used for normal tumble blending. Just a few more examples. I'm conscious of time here, so I'm going to hammer on. So integration of the two control systems. Obviously the blender has a set of controls, and so does your NIR device, and that these can be integrated from a range of not at all the way through to completely autonomous, where you don't even realize that the NIR unit is running in the background. We're going to concentrate predominantly on the perpendicular, the once per revolution, and for this obviously you need a triggering method. The easiest one to set up or to integrate is a gravity switch, which the device will usually have its own gravity switch, and in which case it just needs to make sure that the settings within the device marry up with the speed on the blender for your on time and off time. If you want to go one step further to get a slightly more repeatable, or if you're planning on using multiple different recipes on the one blender, so you're going to be using different blend speeds, for example, then you may be more interested in using the proximity sensor approach, where effectively you put the proximity sensor at the exact position that you want to turn on and turn off, and allow the blender's PLC to do the rest. For continuous triggering, you don't need to trigger. The way that we tend to communicate is between the blender's IPC, industrial PC. We'll use a method of communication called open platform communications, or OPC. This is just a method for communicating between a variety of equipment, and it generally requires an OPC server, which is a piece of software installed anywhere, whether that be on the domain, on the Blender's PC, or on your NIR control PC. And it basically consists of a set of holding registers in which information can be passed back and forth. Then the Blender or the NIR unit effectively become OPC clients, or the software on the Blender or NIR unit become OPC clients, and they populate or read from these holding registers within the server. This is a very busy slide, but it effectively shows that you've got your NIR unit up in the top left, which is connected via Wi-Fi to its control PC, with the control PC plugged directly into the Blender, with the Blender running a Modbus and OPC server, and the NIR unit using OPC UA client software to access that server. And that allows the communication between the two. That's the most basic level of integration. That can be taken one step further, where you effectively have your Blender connected to a domain, to your customer domain. And then your NIR unit connects to your laptop, and your laptop connects to the domain via Wi-Fi, which gives you a lot more mobility at the user end, and means that the Blender can just be run into a permanent domain network. This is our preferred approach if available, but it does mean that there is a much more integration required during commissioning of the Blender. And then the final way, or for continuous sampling, you contain the lot within the Blender, and the Blender gets connected into the domain to allow you to access the control software, or to create models, or to archive data. But other than that, the NIR unit is incorporated into the Blender, and the whole network is effectively local and behind the scenes. Okay, so reasons for why you may be getting inconsistent results when using NIR PAT. One of the most common methods for inconsistent results is triggering. If the scan time for the PAT unit hasn't had the correct delays in place to marry up with the speed, or if it's going at high speeds and missing the proximity switches, things like that. Could be just damage to the site window, which is altering the results, or the vessel shape. If this is a new piece of equipment or a new piece of plant, and you're getting spurious results, review your design of the vessels. As you'll see here, this is a simple IBC lid that could be fabricated a lot more simply if we didn't have the radiused corners to stop compaction. Consider valves that might be fitted, the lids or gasket details. Does powder get trapped around the lip between the lid gasket and the body? Any breathers or ferrules that you've got fitted, or even if this is sort of an inline processor, look for crevices or different gaps where API may be getting trapped and then re-released onto the surface of the product at effectively random points within the blend. And finally, looking either side of the tumble blending process, how else can you integrate? One thing that we've done on numerous occasions is that we can use it to interlock with a batch ID. So confirming the materials as they're being put in against a recipe, validating the recipe as it goes, and validating the batch ID. It can even be incorporated into automated charging systems, where you effectively wheel up a drum, clamp it in place to the underside of your larger production style machines, scan a barcode, and away you go. And then an inline or integrated NIR unit can confirm that the powder being charged is the correct powder against the recipe. Effectively, due to the size of these units now, especially the VRB Micro NIR, range, we can generally integrate them in any way, shape or form that's required in any location. So I think that is enough from me. I think I've run over time considerably. So if you have any questions, please save them to the end. And we will now do a quick demonstration of one of our smaller lab scale blenders with VRV Micro NIR PAT W fitted to it.
Thank you, Sean. So here's a video that we had to record a couple of weeks ago due to the current restrictions, but we'll try to keep it brief, but you get to see actually the PAT in action down at the Pharmatech facility.
Hi there, I'm Sean O'Riordan, I'm the Operations Manager here at Pharmatech, and today we're just going to be going through our agitated blender 15, an AB15 model. This one's using our advanced controls, our level 2 controls, and we're going to be showing you what the blender can do and how we have integrated the controls with the VRV Micro NIR into an agitated IBC vessel, and then Simon are going to take you through the chemometric side and how the software works behind the scenes.
So Sean, what products are we putting into the vessel?
So we're going to do a mix of CMC, lactose and then a bit of talc today.
And this is a 5 litre vessel. Are we? What's the optimum fill level for a 5 litre?
So for all tunnel blending, we usually aim for between 50 and 66%, or for agitated blending, we aim for around the 66 to 85% mark. But that's mainly so that the actual agitator bar is covered and isn't spinning in free air.
Understood. Yeah.
But as a rule of thumb, we'd usually aim for the 50% mark. It's a right-handed job.
Okay.
Obviously, we're not in a labs scenario today. We do have dust-free solutions for charging these vessels normally. So I'm just putting 1.5 kilos of CMC in, 1.5 kilos of lactose, and then probably around 20 grams of talc. I feel more like a chef than a driver. Horribly wrong if my fault density maths hasn't been calculated properly.
Just for those watching, we have actually just sped this up a little bit because it does take a while to fill a vessel properly. So this we've done deliberately to try and show you more of the instrument in action. That's good. Just want to show us the inside of the lid, just so you can see how the NIR is.
So we've got the NIR attached to a ferrule on the lid, just with a simple sanitary style tri-clover clamp, and then we have a sapphire lens that's mounted completely flush internally, bedded into some food grade silicon adhesive, so that is going nowhere. The joy of that style of
fabrication is that if you don't want to use the NIR, you can still use the same vessels.
Yeah, because the other option then is to have a removable flange kit. So if you want to just have one lid that is your NIR lid, you can obviously have that flange kit welded into all the other lids and move it. It's really quick to install.
Make sure it's tight.
Good. Just a standard clamp.
Yeah, just a 3-inch bolt over clamp to hold it in place. And then because this has got the agitator bar fitted, because it's one of our agitated blenders instead of our normal standard multi-blend tumble blenders, and this has got an additional dog clutch instead of just the coupling flanges, and that's obviously to drive the agitator bar. Okay, close the safety guard. Verified over the OPC server if you wanted to. And a batch ID, which again is now verified by the OPC server to interlock the controls. All of that can also be stored as preset recipes, with the vessel ID and the batch ID being the variable that you enter each time. Entering the speed blend parameter in RPM, time in minutes, and then because we've got the PAT device, you have to activate the handshake, and we can already see that the OPC server is working because we've got a PAT device ready. And if in some instances you may want to ignore the first 2, 5, 10 minutes of a blend before you want to start capturing data, in which case you have a trigger delay for the PAT device, which can be set from the blender HMI. Check the parameters, set them all, and press start. Blender will ramp up to its target speed. And as you can see, the PAT device is triggering high gravity. You can tell that by the light activating each revolution.
So what we're seeing now is the live output of the moving block that we talked about at the beginning. As you can see on the y-axis, you've got a very high percent RSD, starting off around 45%, which is quite normal. There's quite a lot of disturbance going off in the first few revolutions. As you can see now, you are generally seeing a downward trend. And you can see block 1, which is actually a 10 block moving block. So looking at spectra 1 to 10. Block 2 is looking at 2 to 11 and so on. And just down the bottom, it's quite hard to see, but it will be available shortly. You can see there's an arbitrary limit being set, which is where the red line is. And the software is given a quite clear red cross to say it's not within the predefined threshold parameters. And eventually, once we start getting down to the parameters that we've set within the software, we'll start seeing the green tick appearing. So we can see now we've reached a threshold eventually, and then the threshold is not just a definitive 1 point. We've set it so it has to be a number of points below a threshold before it activates the blender to stop. So as you can see here, there's been a feedback now that's told the blender to stop. And then these are the final interface showing the blend is complete. So the next part of this webinar and the final part is to hand over to my colleague who's in Italy, Emiliano, and he's going to define a bit more of the software integration that we have and show more of the chemometric side of things as well. So this is especially useful for existing customers who have not seen the latest version of software.
Okay, good morning, everyone. I'm Emiliano Gendorini, the account manager for the Near product in Viavi. Darren, just confirm that you see my screen.
You do, but we just need to minimize our presenter mode.
Exactly.
There we are. Thank you. Over to you. Thank you.
So, my target for this small presentation is to show you some new feature in the software. Let's start with the login to our software. And let's select a device. Unfortunately, I'm not so lucky to have here on my table a PAT-W, so I have just a PAT-U, but it's fine for this demonstration. First of all, this is how the software looks like. We have, let's say, tools where you can have the validation menu, the, let's say, simplified workflow, the user access, and a global setup. I want to point out that in the new release of the software, the 3.2, that it should come very soon, we expect to be live, let's say, around the end of April. We have replaced the old USP 11.19 with the new pharmacopoeia, the new version of the American pharmacopoeia that is the USP 1856. But apart from this one, we have also worked pretty a lot in the side of improving the OPC communication that will enable a smoother, let's say, communication with the Pharmatech blender for sure. But I want to drive you through a little bit the new data analysis package that will be introduced. First of all, we have inside here the possibility to run embedded in the software principal component analysis, PLS, moving block, and spectral match value. So let's start from the moving block that was shown by Darren a few minutes ago and also by Sol. So this is the new Windows. We need to click on new. We need to create a method, webinar, let's call it like this. We need to confirm, let's say, the method, and afterward, going on the right hand side on the screen, let's say there is this box with the calibration set. We need to upload the first method that we want, the first list of spectra. So in this case are 50 spectra acquired at different time. It's not a blending, it's an evaporation, but the consideration that we can get are exactly the same. Here you have the setup. So we are working with only one region, means that we are considering from 908 to basically 1700 all the wavelengths below our spectrum. Eventually, we can also define, let's say, specific region for specific peaks, but let's keep it simple. Let's take one region, and we can apply the moving block that was explained by Darren to the spectra, but eventually also to the PCA, but we will come back to the PCA. So now we stay with the spectra. We can add a preprocessing just to keep it simple. Let's do a first derivative and apply the first derivative to our spectra. Again, we can select in this box the range. It can be a single peak or can be a region, okay? As I said, we want to keep it simple, so let's select from 900 to 1700 nanometer. We can eventually flag to do the calculation not with the standard moving block, but with the F-test statistic. Let's leave it without, and the block size. I made some trial on my data. I think that the optimal number is 10 for the block size, and I click on apply. So basically, this is what Darren explained a few minutes ago. So you have the standard deviation. So in this way, so the variability into our spectra, versus the block. Block or time are exactly equivalent for what we concern. I want to, let's say, step a little bit ahead. We can click on the endpoint criteria, and in the endpoint criteria, you will see a lot of new things. First of all, in this software version has been implemented the capability to reject spectra that are not, let's say, compliance with the spectra that we expect, let's say. And one thing is clearly to reject a certain number of spectra before starting the calculation. This is clearly in the beginning a function that we have been requested from some customers, because in the beginning we have normally a big variability, and I would say senseless or not, I don't want to argue, but if you want to remove that big variability in the beginning, you can select a number here. You can also decide to reject the last spectrum in the calculation. This is probably a more useful thing, because in a lot of cases, the last rotation, the blender is slowing down, and so you can have a sort of artifact. But the thing that I want to point out here is this part, the criteria to, let's say, stop the blender. Basically, we can start from a moving block standard deviation. That is the one that I showed you on the big screen a few minutes ago. But we can have also the moving block mean. That is basically the area that is used to calculate the standard deviation. Or eventually, from time to time, is also pretty useful that we use the RSD, that is basically the moving block standard deviation divided by the moving block mean multiplied by 100. So that's a quite good one, because the moving block standard deviation is normal, a very small number, very difficult to understand, to have the right feeling. The RSD is a percentage. So, for example, we can set here 10%, and when we do save limit, you see the famous threshold that was demonstrated by Swan and Darren during the presentation, during the video. But this is something that was already possible in the past. What is the new stuff into our software? We have the possibility to introduce more than one batch and to compare the profile of more than one batch at the same time. This is a really important option, because clearly when you have such a kind of profile and you are in a formulation lab, you can, let's say, see that the product is going to is mixed at a certain time. You can see that the value is below the threshold, but it's really important to be able to compare, let's say, if one blending is behaving better than another one in the formulation lab. When you go to the production and you are moving from a batch verification that is done in the beginning on 3 batches to a continuous process verification, you need to compare every single batch with a so-called golden batch. Let me try to explain you a little bit how it works. So you see here we have one batch, is the batch 1. Now we can retrieve other batches that I prepared for this webinar. So let's get the second one in here, and you see that is colored in a different way. Let's go to get the third one, and it's another color again. And now we go get the fifth one here. And you can see that the spectra are similar, not exactly the same. I apply now the moving block, and you can see here that you have the different 4 profiles overlapped. And from this menu, you can select the one that you want to visualize, but look at this, this is a surprise. The yellow line here is basically the average of our 4 batches, and it represents in a certain way the golden batch, the target that we need to go and to follow during our process. And the other 2 dashed line, the red and the blue line here, these are the limit, the maximum and the minimum limit where our spectrum or our project should stay inside. And this is very important because, for example, if I select the batch number 1, I see that is tracking here very close to the upper level and afterward goes down in here. But I can do the same, let's say, for example, for the batch number 2, where I can see that is a little bit bumpy in this area here. Obviously, the NIR is, let's say, registering something happening into the blender. Afterward, we need to discuss together with the, let's say, pharmaceutical technician what can be the reason. But the NIR here spot clearly a certain level of difference. Clearly nice, but it's also important that when you are in this side here, you can also create a validation set. In the validation set, I'm going to upload other 2 batches, the number 7, okay, and the number 8. The number 7 is a batch that I made with the idea to be, let's say, a right one. The 8 is a batch that I create an artificial, let's say, variation. In fact, when I click on apply, okay, I see here that I need to select, let's say, the batches that I want to use for the golden batch calculation. And now you see that I have calibration here, but I have also the validation menu. And when I select the validation menu, the golden batch and the limit are the one in calibration, but the batch number 7 and the batch number 8 are projected on the golden batch. And this allows you to clearly understand that the Azure one is, let's say, starting a little bit higher from the beginning, but in a certain level from here on it goes into the specification that we are expecting. The blue one started very similar to the golden batch, but artificially we created something, and you can see here very well how this is behaving. There is a variation, it goes up, and afterward it takes a lot of time to go down into the specification. This is really important to consider, because like this we can really play and understand from the graphical point of view what is going on into our blender. All of this obviously can be connected with the endpoint criteria. We have already saw that we can define the limit. Obviously, if you have to define the limit, I personally feel more confident to see one spectrum at a time, because otherwise it's more complicated. But I want to go back here because also here I can show the golden batch and I can show the maximum and the minimum. Last but not least, in this screen are the advanced criteria to stop the blending. As Darren said, it's not enough that one single point is into our specification, but we need to have, for example, like 8 out of 10 points into the specification, and we can define it here, or, and this is a function that was already present in the 3.1, but eventually we can also say that continue for 10 measurement after the endpoint is has been let's say achieved. Well, here is 10 out of 10 in a certain way. Clear, another thing is that here we are referring only to the moving block, but we can have obviously a multiple region criteria where we consider at the same time together, let's say, not the data from one region, but the data coming from more than one region. And this is a thing that we really like to consider. And well, another thing that has been introduced is that more from the technical point of view is that we can save the spectra into the data. We can also protect the model with a password and keep it stored. But I want to show you another way that is not the moving block, but is the principal component analysis to, let's say, follow a process. Let's call it with the same name, webinar. I confirm, I create here a calibration set where I add, for example, the batch number 1. Okay, spectra, as we made before, just a simple first derivative. I can select the region. I leave it as it is by default, and I do a, let's say, validation, a cross-validation with the leave one out. Let's do 10 principal component analysis, and here you are, the let's say the classical PCA result. You can see here, especially for the process control, the score plot where we have PC1 versus PC2, and if I right click here, I have an interesting function that is group spectra by sequence, and if I say that in my case are 50 spectra, I want to have 10 group, each group will be 5 spectra, and like this I can have a let's say color that is visualizing very well the let's say the number of spectra. Obviously, if you are keen, you can go here, you can use the show tooltip and one by one see what is the sample name. Not so convenient like in this case. You can also see the line, the clear, this is the PC2, and this is an interpretation very similar to the one that we have in the moving block. So when the PC1 is no longer changing, okay, obviously the PC1 can be close to 0 or close to a certain number. Actually, it should not be close to 0, it should go to a certain number. And you see here that basically from 35 going onward is done. Clearly, you can also see the PC2 or the other principal component. If we go back to the scatter plot here, we can also think that now we can define a validation set, and from the validation set, let's retrieve the batch number 2, and let's compare, let's say, the batch number 2 versus the batch number 1. I'm sorry, I need to select test set, and now I regenerate the model. Instead of using a cross validation, I'm using an external test set validation. Now, if I just right click here, I can see in blue the original process, the first batch, and in red the second process, and you can see here that around this point the two processes are converging. Obviously, I can also plot the line and see that, for example, this is the principal component 1 of the original first batch, so of the calibration set. I can quickly slope to the validation 1, and you can confirm that from here onward the process is over. Obviously, you can have a lot of consideration. You can, let's say, do whatever you want in terms of principal component analysis, including defining, for example, how can I say, yeah, like this. You can define, for example, a note-linked square, okay, that is defining the interval of confidence, okay. And we can say that once our, let's say, points are into this ellipsoid, the process is something that can be, let's say, considered done. Obviously, the size of the ellipsoid should be somehow adjusted as we wish. So there is anyway a certain level of personal interpretation. I want also to show you that we have introduced in the principal component analysis the endpoint criteria. And the endpoint criteria, they obviously in the principal component analysis using the auto-linked square in confidence level. And we can select, for example, 99, 95, or 90. and change the diameter of the ellipsoid. And this can be applied to the first principal component only, or can be applied also so in the two-dimensional scatter plot, or eventually we can define a principal component using a line. So this is more your, let's say, decision, which one you feel more confident. Saying that, I also want to point out that once we have saved this model, let's take the original without the validation, that is faster, we can eventually go back to our moving block model, called webinar, and once the method has been uploaded, like in this way, we can go in here, and instead of applying the moving block to the spectra, we can apply the moving block to the principal component analysis, and we need to select the model that we have just calculated before. We can click apply to the component 1, and all the consideration that we done before on the golden badge and so on are clearly available also in here. This is the validation profile with the blue badge that was the one artificially wrong, and these are the principal component 1 moving block that allow to better interpret the moving block, the PC1 variation over the time. From my side, Darren, I think that I have completed the demonstration on the software. I hope that was clear enough. Otherwise, I'm available for any information.
Thank you very much. Thank you very much. I think that concludes the webinar. Apart from, does anybody have any questions?
Right, thanks guys. Yeah, we do have a couple of questions, and for those who are watching and who do wish to ask any questions, please just use the Q&A section on the screen. So, right, a couple of questions, and well, the three of you can decide who will answer. So the first one is asking, what is either the smallest or the largest kind of blender that you can apply this sort of PAT testing on?
I think I'll put my head above the parapet. I think the smallest one I've seen was on a 50 milliliter vessel, and obviously we've designed and fitted that. And I think the largest I've seen is one. I mean, Sean, you might be able to help here. Probably 1 cubic meter IBC or bigger. That's the great thing about the PAT. There's no real limitations of which size vessel you can put it on.
Yeah, I've seen these on 500 litre V shells, 1000 litre, 1500 litre IBCs. There is no upper limit if you're going on once per revolution, really. And yes, Darren, the 50 mil pot is about as small as we can get it, mainly because you're down then to the diameter that is a similar size to the actual lens on the micro NIR.
All right.
And actually, one of the advantages, Darren, of the micro NIR, in my opinion, is that you can really go from the really small one to the biggest one with the same device, and that's clearly an advantage because the device, including the battery, is less than 1.5 kilos.
Yeah, yeah.
So scalability is a key point.
Okay, thank you.
Okay, back to you, Darren. You can decide who answers this one. Is there a solution for operating in an ATEX environment?
Answer is yes, there is ATEX certification. So again, yeah, just get in touch if that's something that you want to discuss. But we do have ATEX PATWs available. Yeah.
All right, thank you. Well, there's been no further questions published, so over to you, Darren, to wrap up the meeting and the webinar.
Okay, so first of all, thank you to everybody involved. Obviously, Sean and Emiliano, and if anybody has any more questions that want to follow up after, by all means get in touch with Simon, and I'll collect the questions to the relevant people. Thank you.
Thank you.
Thank you for the invitation, and thank you to all the attendees.